So there we go. Okay, thank you so much for the invitation. I'm very happy to give this talk in here. And so I'm going to talk about pretty much what I've been doing for the last 10 years or so in inverse problem from the point of view of scattering. So it's going to be less about a particular single question where I will give an answer, and more about this kind of story of, what we've been doing over the past few years. So if you are interested in some of these questions, please ask me by email later or after the talk. I will be very happy to talk about more of these. Anyway, so first I have this mandatory few slides of what is scattering theory, how do we view it, and so on. So in my point of view, I consider scattering theory of fixed frequency. So the idea is that there's some incident wave or incoming wave that hits some type of object, which in this slide is going to be, so in this presentation, it's going to be a scattering potential. So it's a wave that can penetrate inside and through, but gets perturbed by it, and the perturbation then come out as a scattered wave. And if you sum these two things up, you get this physical total field, which satisfies, for example, this fixed frequency Schrödinger equation. So there are many people working on different equations, the same type of ideas. So I will be mostly talking about this equation. Okay. And for those of you who don't know so much about scattering theory, so here is the same thing of the previous slide, but in a picture. So on the top one here, we have the total field, the physical thing that you can measure by putting some sensor. For example, if you are doing acoustics, so you consider this Helmholtz equation in acoustics, you can go put a microphone somewhere and it will tell you the value of this field. So then you think that this is the sum of an incident wave. So what would be the wave if there is no object? Plus what is the rest? And the rest is the scattered wave. And you can see that in this particular case, the wave was coming from the left. So you can see there is some point here and some shape here, and it started scattering further. And so here is this scattered wave again as a picture. And so if you zoom out in this, you imagine you zoom out further and further, you see that these circles, like in the middle here, there's a clear, corner. Here is a bit more round. And then as you go further and further, this wave will look more and more round. So they will be looking more and more as the wave from a point source. Maybe if you have good contrast in your screen, you can see that there's a difference. So if you zoom out very far, you will see that in here to the right and to the bottom, there is more contrast between the blue and red than, for example, in this direction. So this contrast in different directions, that is what is measured in an inverse scattering measurement. So it is called the far field pattern or scattering amplitude, or there's several other related concepts. So the scattered wave will be this kind of in the far field. So you will have the far field pattern, which is the contrast, and then there is the shape of the wave, which is what the point source would create. Anyway, so also a little bit of history. So in inverse scattering, you have this far field map. So you send an incident wave and you recover the scattering amplitude or the far field, and you want to recover some information about the scatterer. Maybe you want to recover the whole scattering potential. Maybe you are just interested in at least getting the shape of its support. So this is again some very old history. So if you go back far, so if the full far field map is given for all large frequencies, meaning that you are able to send every single type of incident wave at every single large frequency, then you can determine the scattering potential completely. So this is by Saito in 84. Then there was a big open question of what if we only have one large frequency, or doesn't need to be large, any one fixed frequency. And this is related to the Calderon problem. So the inverse problem for the conductivity equation, it's related to other things. So this was much more difficult, and it was solved in 3 and higher dimension by Sylvester and Ullman in 87. Novikov published a related paper in 88. And also, so my PhD work was related to the paper by Buchheim of 2007, where he solves the scattering problem for in 2-dimensional space. So the method of these 2 previous papers only worked in 3 and higher dimensions due to some algebraic fact. But Buchheim used some slightly different method using a different type of solutions, and that worked. Anyway, so for this situation where you can send several different incident waves, but you only have one fixed energy or frequency, it has a lot of variation. I cannot talk about all of them. So my focus on my work for the last 10 years is on a single measurement case. So you're only given the scattering amplitude for a single incident wave. Depending on the problem, you can maybe decide for yourself what kind of incident wave it is. Maybe it is given by, the nature. But the point is that there's only one single wave, and you have the far field pattern of that. And so this is related to a problem that's still open, called Schiffer's problem. Can a single measurement determine the shape of the scatterer? The reason why people talk about shape is that if you do this kind of naive dimension counting argument, like what is the dimension of the data that you have? What is the dimension of the far field pattern? It will be n-1. And if you have a potential, it will be a function of n variables. So you would think that there's no hope of determining a function of n variables from a function of n-1 variables in a continuous way. So that's why people are thinking that, okay, maybe we can't determine the whole function. Maybe you can determine the shape of its support, which would also, naively counting, be like an n-1 dimensional object. Well, so then there's the question of why only one measurement. One answer is that, okay, the multi-measurement thing was solved, and as a young researcher, you have to go into newer problems. But there's also some applied and theoretical motivations. So from very applied, if you think of what physicists are doing, so this is an old experiment, Lord Rutherford's Goldfall experiment. So in this experiment, there's this kind of vacuum chamber. There's a box with a radon here, and the radon emits some alpha particles. And here, the F is a thin foil of gold. So when the alpha particle goes here, it's very thin, this foil, so maybe it can go through without hitting anything, but it might also hit an atom, on the foil, and then it might scatter in some direction. So then here there's a microscope and a detection screen, and when this scattered alpha particle would hit the detection screen, it would create a brief flash of light. And then what they did is that they moved this microscope around. Here's like Lord Rutherford looking into the microscope, but it was most likely, his assistant. So would move the scope around and count how many flashes of light per minute, let's say. And in directions when there is more scattering, there will be more flashes of light per minute. And in direction where there's very little scattering, there will be very few flashes of light. So in that way, they were kind of measuring the scattering amplitude, like the faceless scattering amplitude, using this kind of single measurement. So in this case, if we think of this modeling, if we model this using some kind of nowadays more like quantum mechanics or something, it would be a single incident wave which corresponds to this radon source here, and you are measuring the scattering amplitude in all different directions. And in that case, this one measurement gave a lot of information. They knew that before this experiment, physicists were thinking that the atom would look like this kind of cookie with the protons in this kind of like soup of electrons, or vice versa. I'm not too sure. I'm not a physicist. But after this experiment, because they noticed there's quite a lot of backscattering, like quite strong backscattering every now and then, so they deduced that there must be like a quite dense core which makes the alpha particles, bounce back, but most of the time they will be not reflected so often. So if you have one measurement and you have some good a priori information, you can reach some very good conclusion. So that's kind of the applied reason of why to look at scattering with one measurement. It's cheaper to just do one measurement and you can still get good information. Anyway, so if we go back to the inverse scattering problem, even with multiple measurements, there's some like numerical methods called, for example, sampling methods, where the idea is that, okay, you have the far field operator, so you can potentially have multiple incident waves that you send in and measure the far field. But then using some numerical methods, you would then want to determine some, like, for example, the shape of the scatterer. I'm not sure if the sampling method can tell you the value of the scattering potential, but you could definitely tell the shape, where is the support located. So there's this old method called the linear sampling method, 96 Colton and Kirsch. So they kind of sample the space with points, and then using the measurement from the inverse problem, they can then determine which points are in the support. Ikehata had a so-called probing method where you can probe with different curves and you would know which parts of a curve belong to the support. Then many other people, Luke, Pothast, Sylvester, Gusiak, they did range tests or no response tests, which you could in some way classify all in the sense that you're trying to measure, trying to determine where's your scatterer by probing it with sets in some way. Then another type of method is called factorization methods. So factorization method is kind of like a sampling method, but it gives, so sampling methods only gave like sufficient condition for when this point belongs to the support, but factorization will give necessary and sufficient. And the rough idea of the factorization method is that if you have some incident wave, which is a Herglotz wave, meaning it's a superposition of incident waves, of incident plane waves from different directions that you weighted with an L2 weight from different directions. And here you have, the corresponding scattered wave. Then the far field operator, so that's the operator that takes this G, which is the coefficient of how you are superposing those incident waves, and gives out the scattered amplitude. So gives you the contrast at infinity. So this far field operator in the factorization method, it can be factorized into this product of G, T, and G star. So the dual of G, where G is a compact operator and T is an isomorphism. And the range of G can be characterized in this theory, and it will give you some information about the support of your scatterer. So to those things, there is some related concepts. So called transmission eigenvalues, or yeah. So if you assume that now you are looking at a single incident wave, and you assume that the far field is 0, so it seems that there is no scattering, then you can use tools like Rayleigh's lemma or unique continuation. You can see that if you don't notice scattering in the far field, there is actually no scattering. So you can determine that the scattered wave is 0, all up from infinity all the way to the boundary of your scatterer. And then inside the scatterer, you have this equation for the incident wave, the wave that doesn't, you know, that would be there if there was no scattering object. And then you have the total field, which is the incident wave plus the scattered wave. It satisfies this physical equation where there's the potential. And then you will also know that because the scattered wave is 0 outside of the obstacle, so it's Dirichlet and Neumann data are 0 on the boundary of this obstacle or of the scatterer. So then if you said that V is this incident wave and U is the total wave, V and U solve the so-called interior transmission problem, meaning that K squared would be an interior transmission eigenvalue. And so those interior transmission eigenvalues, they will cause problems for the sampling methods. So let me go here. So interior transmission eigenvalue is also a field of research where I spent some time. So it started like in 86, 88 by Kirsch and Colton Monk. They posed this problem for interior transmission eigenvalues. So then there's also, of course, so it's like an non-elliptic, non-self-adjoint spectral problem in some sense. So of course there's this question of discreteness, existence, you know, quantity and so on. So it took a few years for discreteness to be proven by Colton, Kirsch, Päiväranta, and Rinne Sleeman. Then after that, for almost like 20 years, 15, 20 years, there was like not much published around it. And after that, there was like quite an explosion. So in 2007, 2009, Ciccone, Colton, Monk, Ciccone, Colton, Hadar, they proved that you can get some information about the potential from these interior transmission eigenvalues. Then, you know, after that, people were like, oh, these things are actually interesting. We should maybe study more. So there's the existence for general type of scatterers, the existence of infinitely many. There were some results showing that you can calculate, you can deduce these if you know the far field data. So if you have the scattering measurement. And also then there was this results about where they are located in the complex plane. So transmission eigenvalues, you can consider, you know, real ones, or you can consider complex ones. And then after 2010, you know, I lost track. There's just too much going on. And then also more recently, people have been studying these Teklov eigenvalues, which kind of satisfy the same kind of like history that they are useful for scattering theory. Anyway, so the point is that interior transmission eigenvalues versus sampling methods. So if the incident wave is non-zero and the scattering amplitude is 0, then K squared is an interior transmission eigenvalues. And people that use sampling methods, they avoided, you know, these transmission eigenvalues. So they avoided working with these frequencies where this happens, because they rely on the far field map being injective. And the question is, are they too careful? And you know, the answer is that in some way, no, because there is some actual examples where you can construct some potential and some incident wave, where indeed there's an incident wave, there's a potential, but there's no scattering. So this is an actual situation that can happen. But then, on the other hand, from those results on transmission eigenvalues, you know that like most potentials that you are considering, they will have transmission eigenvalues. Does this mean that, you know, for most potentials, you know, sampling methods, factorization methods will not really work? You know, what if your frequency is a transmission eigenvalue, you know? So that's a big worry. But then this is the paper that started like all this research for me. So with Päivärinta and Sylvester in 2014, we looked at this very particular type of potential. So it's basically a smooth test function, which has like a 90-degree corner. So you have a smooth test function that you've restricted to a quadrant. And you assume that the value at the origin is non-zero. So there's a jump at the origin, a corner singularity. And we say that this always scatter, meaning that no matter what is the frequency, what is the wave number, there will be non-zero scattering if the incident wave is non-zero. So in other words, the far field map is injective at any wave number k, at any frequency k, even though this potential has transmission eigenvalues. So this kind of work showed that this sphere that was coming from transmission eigenvalues does not need to go all the way to the injectivity of the far field map. There's, however, when doing numerics and so on, so if k happens to be a transmission eigenvalue, the far field can become arbitrarily small, even if you have some lower bound for this incident wave. So even though it cannot become zero, it can become arbitrarily small. So that's a good thing to keep in mind if you are working with the far field map. Let's see, I have about 20 slides and 30 minutes. So, no, how much time do I have?
You can take, you can finish it in 55 minutes.
Oh, okay, yes. So I will give a rough sketch of how to prove that, this kind of potential always scatters. So the idea is that, okay, you take some incident, you have fixed frequency, you take some incident wave ui, and you assume that it doesn't scatter. So it's a proof by contradiction. You assume that it doesn't scatter, then you can deduce the scattered wave is zero all the way to the support of your scattering potential. So u is equal to ui in the complement of your support. Then you can look at this kind of integral. There's the potential incident wave, and then there's u0. U0 is some arbitrary solution to this equation inside the domain. Using the equations for ui and u0, you can deduce that this is equal to this formula where there's the scattered wave here, and this one will be equal to 0. There might be some boundary terms, but you can deal with them, no problem. This is just a sketch. Anyway, so then in the simple case, we can separate all of these functions. So incident wave, we separate it as the value at the origin plus the rest. In more complicated case, you would have to take the Taylor expansion. For example, if ui vanishes to 5th order, you will have the 6th order term here. So that will be more complicated. But in a simple case, ui does not vanish at the origin, and then you take that value here plus the rest. For u0, you select one of these so-called complex geometric optics solution, which rho is a complex vector, so that the absolute value of this thing decreases exponentially in the direction of your potential. So at origin, this will be fixed constant 1, but then in the direction of your potential, it will start decaying exponentially. And then also you assume that your potential inside the corner, there's the value at the corner plus some remainder. So you need to have at least like Hölder continuous potential inside the corner. And now if you do this split and you look at this integral here on the left, you take all these lower order terms on one side, which is here in the middle. You calculate this integral, and you get this kind of very simple estimate. So there's the absolute value of rho to the power of -n. And then all these other terms, you use some Hölder and LP estimates, and you can see some bound, which is like this -n minus delta for some positive delta. The difficult technicality is here to have a good enough bound for this second term here in the complex geometric optics solution. So that is something that we need to do a lot of work back then. And you can see this is a contradiction because, you know, the thing that is bigger decreases more rapidly. So you know, you reach a contradiction, then you can see that, okay, that means that in fact this thing scatters. The scattering is non-zero. Anyway, so this was kind of you know, on the last year of my PhD work, I was doing that. Then there's several other people who took this kind of problem and a question, and they started like generalizing it. So you could consider, it doesn't have to be like 90-degree angle. You could do any angle in 2D, 3D. You could do almost any spherical cones. An interesting result is this from Huusala and Vesalainen, that you could use this type of method for doing what I call polygonal scatterer probing, meaning that if you know that if you know a priori that your scatterer is a potential that's supported on a polygon, on a convex polygon, one single far field measurement is enough to determine the shape and location of this polygon. Anyway, so yeah, so there was a lot of like, so in this proof that I had here, I skipped all the technical details which involve proving this lower bound. And the problems come from when your incident wave can vanish, let's say, up to some finite order at the origin. Like maybe you have a Herklotz wave instead of a plane wave. And then it's the shape of, you know, this corner. So all of these cause a lot of technical problems. So that's why there was a lot of work done on like increasing the geometry that we can handle. And then there's more recent methods which they use this so-called free boundary methods, which deal with more general geometry, but then they have some restriction on what type of incident wave can be there. So there's a lot of like different results working around this. Okay. Anyway, so this is now back to so from this list I was like skipping my own work. This is again in more detail this polygonal scatter probing. So this is not my work, but Vesalainen was my office mate back then, and I was following this work a lot. So this is in more detail. What does it mean to probe? So if you have two different convex polyhedra, P and P prime, and you have potentials which are supported on them for admissible functions. By admissible, they need to be Hölder continuous up to the boundary of those polyhedra, and they cannot vanish on the corners of those polyhedra. So it's 2D and 3D, polygons in 2D, polyhedra in 3D, and I think more recent results do this also in higher dimensions. So then it says that if those two polyhedra are different, then for any non-zero incident wave, the scattered amplitudes will be different. So you cannot even force you cannot somehow engineer a very complicated incident wave such that from the far field these two polyhedra will look the same. And that means that, at least on a theoretical level, a single incident wave would determine the shape and location of this polyhedron. And as an interesting note is that if you look at Ikehata's enclosure method, so he had a paper from 1999, which also talked about polyhedra shape determination, and it kind of gives roughly the same, slightly different context, like the different assumptions. But in that paper, they also considered one measurement situation. Anyway, so I was very interested in this result, and then with Professor Hongyu Liu, we started looking. So this was published in 21, but we started working on it already in 2015-16. So we started looking at stability for this result, and our stability is not optimal. But we basically showed that the Hausdorff distance between these two polyhedra is like a double logarithmic bound between the difference of the far fields of that they create for the same incident wave. And we also had to make these technical assumptions that the far fields do not vanish in the region where we know that the polyhedra are. So if you know from like multiple wave inverse scattering of fixed frequency, if you determine the potential, the stability is logarithmic, and that is optimal. In this case, there is double logarithmic. So we don't have an example showing that you need double logarithmic thing, but we have a strong suspicion that you cannot get better than this for the shape reconstruction using only one incident wave. Okay, but yeah, as we said, we have not proven the optimality of this. So then continuing to work on this stability matters, we could use kind of the same techniques to prove like a lower bound for the far field pattern. So if you have some kind of incident wave that is a normalized Herlotz wave, meaning it's a superposition of incident waves, where you normalize it so that the G here, the weights are normalized as 1 in the L2 sense. And you have a potential with a corner, then you can prove some lower bound for the scattering amplitude caused by this incident wave, and it will be, so we know already from previous work it's not going to be 0. So we can prove some lower bound that depends on the potential itself and on P of n. So P of n here, it's the polynomial, which is the first non-zero element in the Taylor expansion of the incident wave at the corner. So if you know that your incident wave does not vanish at the corner, then this is just depending on some constant. So you will have the constant here. But if it vanishes, let's say to 5th order, then there will be a 6th order polynomial here, and this will be the norm of that. But yeah, so then I forgot if it was 2016 or 17 or so, but we had a conference in Hong Kong, and Firaba Chaconi was there and listening to our talk, and she told us this thing about if you have a transmission eigenfunction and you approximate it with incident waves, so as we've proven, you cannot get 0 far field pattern, but you can get it arbitrarily small. But here we just proved that there is this kind of like lower bound, and so we were linking like, okay, did you have a mistake here? So we were very afraid. Sometimes you can make a mistake in your papers, and turns out that there was no mistake. Of course, this lower bound depends on many things, so we went very carefully through all of that and see what it depends on. And it turns out that this allowed us to prove a new type of result for these transmission eigenfunctions. So now if you look at this kind of potential, which is in some domain that has corners, so you're looking only inside the domain omega now. You don't look at scattering, you just look at the PD inside the domain. And if you have V and W transmission eigenfunctions, meaning that V satisfies the unperturbed equation, so there's no potential, there's just Laplacian plus k squared. And if W satisfied the equation with the potential, and you know their difference are in this H20, meaning they have the same Dirichlet-Neumann data. So if we assume that one of these functions, v or w, is C alpha smooth near a convex corner, then both v and w have to vanish in that corner. So let me, yeah, so this is like a numerical result where we're calculating this. So here we have this kind of kite-shaped domain, and we displayed here, I think it's this v transmission eigenfunction. I forgot for which wave number. I think the potential here is just constant, might be constant 2. So we calculated a few of these transmission eigenfunctions, and we see that indeed in these corners it vanishes, these convex corners. But what was interesting also is that in this corner, which is, first of all, it's not convex, so our theorem does not say anything about it. And second of all, it's not Hölder smooth, because there's actually a singularity, like an explosive singularity in this case. So this was one of the first results. You know, there was a lot of these results on transmission eigenfunctions, on eigenvalues, but this was the first one which talks about properties of the eigenfunctions themselves. How do they behave near certain type of geometry? And so yeah, this was work from 2017-16, and so we could prove this result. There's some things that I'm not too happy about it. Like if someone can generalize this, I would be very happy. So we need to assume that there's this C alpha smoothness of V near the convex corner. So that's an extra assumption, because normally you only assume that V and W are L2 functions whose difference is in this H20. So that's the normal assumption. So we have to take a bit more extra smoothness assumptions. Would be nice if the smoothness assumption can come from some theory, we don't know. And the second thing is we only can consider convex corners. We cannot deal with these non-convex corners, so we have nothing theoretical about these singularities that can happen there. And numerically, we've observed that, you know, the level of singularity and level of vanishing depends on the angle there. So if it's a very narrow convex corner, it's going to vanish to very fast. And if it's a very spiky non-convex corner, like up here, the singularity is going to be higher. But yeah, there's no theoretical investigation about that. Anyway, yeah. So then the same, so this is related to the potential probing. I'm going to not give too many details about this, but we could prove this kind of result where you know, if you know a priori that your potential is in some grid of pixels, for example, this thing on the left, if you know that, you know, there's a grid of pixels, you can, with one measurement, like one far field measurement, determine the value of the potential inside each of these, you know, going inductively. Or if you know that, you know, the geometry is nested like this, so it's piecewise constant in each of these, it's one single value. You could kind of come inductively from, you know, from the boundary to the inside. But the difficulty is that that method cannot, like, you have to know very strong assumptions about the rough structure of the geometry. If you only know that it's piecewise constant, you cannot go further. For example, it cannot distinguish between these two things. The problem is here is that here, if it's one constant on V1 prime, another constant on V2 prime, then the potential inside this corner here, inside this 90-degree corner, is not going to be Hölder. It's going to be radially Hölder, but not angularly Hölder. So the stability thing is a very flexible thing in this work. We went further looking at we were thinking that, okay, stability seemed to work previously for many interesting topics. But what if, let's say, instead of a corner, we have, let's say, something with high curvature? Because, you know, you can approximate a corner, like a sharp corner, with something smooth but high curvature. And we could prove a very technical result, saying that if you have a domain which has, you know, smooth boundary in this point here, so there is no like geometrical singularity, and you have Hölder's move function on one side of it, and it's, you know, 0 on the outside. You know, the scattering potential is 0 here, and some Hölder function here. Then if let's see, if so there's two things here. There's like the curvature here, and then there's the value of an incident wave. So if the incident wave does not vanish, and the value of the incident wave is large enough compared to the curvature given by this formula here, so K is curvature, then the far field pattern, which I've denoted as U infinity, is going to be non-zero. So this result is here written for the for the source scattering, but it works equally well for the potential scattering. It's just a bit more technical to tell it. And this was very technical. We needed to somehow analyze the Fourier transform of the characteristic function of this region here. And so in a sense, we could not talk just about curvature itself. We had to talk about, we had to take some extra assumption about how the third and fourth order Taylor expansion of you know, the graph of this boundary behave in a sufficiently wide enough neighborhood. So if someone is interested in this, and you know, has experience of, you know, like stationary phase method on like domains with different shapes, that will probably lead to better results for here. Okay. So one interesting topic is also, so we were spending all this time talking about, in such and such case, you know, you will always have scattering. But from an applications point of view, it can be interesting to have some wave, some potential and some wave, or maybe some source, which does not scatter anything into the far field. So that can actually be more interesting. It's a difficult question. So then, well, technically it's simpler to consider the source problem. So you have some source that has energy and it radiates to infinity. So here's the Sommerfeld radiation condition for U. So U is the total wave. So the question is, if either you can maybe want to determine F, or you might want to find an F which does not radiate. But both lead to this question, like, can F be non-zero, but with the far field equal to 0? And in this technically simpler case of source scattering, it's very easy to calculate what is the far field pattern. So if you take the far field of U at frequency K, it's just going to be the Fourier transform of F restricted to the sphere of radius K. And then some constant that depends on K and dimension. But basically, it's the Fourier transform restricted to a sphere. So the question is, can a compactly supported function have Fourier transform that vanishes on a sphere? And the answer is yes. I mean, there's some known examples. If you take, let's say, F to be the characteristic function of a sphere, you calculate this Fourier transform, it's going to be this kind of Bessel function of order n/2, evaluated at K times R0. R0 is the radius of this disk. And so this Bessel function has zeros. So if at some, wave numbers, the far field will be completely zero in this case, but it's the radially symmetric case. So this is a pretty interesting question in the sense of like harmonic analysis, like what kind of criteria can you give for functions so that they vanish or don't vanish at, for example, the unit sphere, like so that their Fourier transform does not vanish on a unit sphere. And I don't know, it's maybe slightly related to this, but not too directly. But so for those of you who haven't heard, but in arXiv, there's been now for a while, someone claims to have solved this Fourier restriction theorem, which concerns, evaluating LP norms of these kind of things. So that's pretty interesting. But I don't know yet how it relates to these problems. Anyway, so back to this example. So this Bessel function, if you look at where these zeros of this Bessel function are located, they are not located at the origin. So there will be some distance away from the origin, meaning that if the radius of this disk is small enough, there will be scattering. So in other words, a small uniform ball source always scatters. And we found that, okay, it doesn't need to be a ball. Any kind of source which is completely supported, as long as it's small enough, like its radius is small enough compared to the wave number, it will all produce non-zero scattering. There's a lot of like technicalities, but the proof is not too long. So if you have so you can have some complicated actual scattering potential, scattering source, but it has one component that's separated from others. So you have one component that you can go from infinity with a so it shouldn't be like inside, so it's like a multiply connected domain. It has to be like, you have to be able to draw a path from this component to infinity without touching the support otherwise. So if that component happens to be small, so its diameter to some power alpha, which is a Hölder constant, if that is smaller than some norms that depend on what kind of potential you have. If you let's say, in a simple case, if you have constant constant source, but you vary the shape, then this is just going to be a constant that does not depend on the shape. So if you have a constant source restricted to some shape, if the shape has a component that's small enough, there will be non-zero scattering. Okay, so I have 5 minutes. I think I will, it's a bit long to tell. I'll leave it here. So this has more or less all the details. So if you're interested in the proof, you can see it from this slide. I think you can see the idea maybe better here than from the paper. Maybe I can say a few words. So the idea is that you start looking at, okay, it's a bit complicated. Yeah, I don't think I have time, but I'll leave this here for a bit. So in the recording you can watch it. It's not too complicated. You don't need any too difficult analysis for it. Okay. So there we were looking at the small source case, but we can also think of, okay, if we, let's say, avoid small sources, or if we use small sources, can we somehow determine shape using them? Because small sources somehow encourage scattering, at least in this model. So now f is again some function that is supported on some domain omega. And we have the far field pattern, which is the Fourier transform restricted to the sphere. Can that determine the shape when k is fixed? So what was known before is, convex polyhedral shapes. The answer is yes. It works also in elasticity. It works in electromagnetism. So it works in many cases. Then we had this paper about with the curvature paper. We can see that if your shape is a convex polyhedral shape where the corners have been somehow smoothened out in a particular way, if you have two different shapes with the same far field pattern, then the shape have to be kind of close to each other. So they have to be like within a neighborhood of each other. And then also using this result for small scatterers, like small sources, we could show that if we know a priori that omega and omega prime are so-called well-separated collections of small scatterers, meaning that there's an upper bound on the individual components' diameters, and there's also a lower bound on how far a scatterer can be from each other, then we could prove that then there's this both sources have the same number of components, and then the components have to be like almost like touching each other. So they're very small, but they're like pretty much on the same location because they're like well separated. So there's some other recent work using some other method that got a similar result. So it's interesting that this gives it too. Anyway. Yeah, then more about geometry. So if you go more into this kind of harmonic analysis way, we could find some kind of like criteria that if you're looking at cones in 3 dimensions and the cross section is then a 2-dimensional shape called K. So if the characteristic function of K is in a Sobolev space with tau greater than half, then potentials of this form, so potentials that are supported on this kind of cone, will like always scatter, when as long as the potential is non-zero at the corner. Oh, actually, yeah, no, technical detail, yeah. So this is not, so this is like a generic result. So if you have this kind of weird shaped cone, for any delta, you can find a cone in the neighborhood of this, in the sense of Hausdorff distance, such that this new cone always scatters. Yeah. And if you look at the source problem, you can actually prove an exact result, saying that if you're looking at a source instead of a potential, you can prove, for example, that thin enough. So if you have a cone which is satisfying this condition I had before, and it's a source, it will produce non-zero scattering. But we also found an interesting result that if you have a source that has a cone like this, which is thin enough, meaning that the cosine of the angle here has to be less than 1 divided by square root of 3, then no matter the shape of this, it could be smooth, like spherical, or it could be like a fractal, it will produce non-zero scattering. So again, like somehow these kind of weird shapes, small shapes, sharp shapes, tend to always cause scattering, theoretically. And more recent result is the same thing holds for like screens. So for example, a flat screen in 3 dimensions, like 2D screen in 3 dimensions, as long as it's flat, will always produce scattering. Yeah. Okay. There's some question about the future topics that we're working on, but I think I'll stop here. I have my time ended. Thank you.
Thank you very much, Emilia, for the very nice talk. Thank you so much. Thank you. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments, please? Emilia, if not, could you please say a few words about your future works, if possible?
Yeah. So There's some future work about these. They are very difficult questions. So I have a few of these questions that I'm thinking of the most. The thing that I'm most hopeful could be solved one day is that when looking at these corner scattering situations, we always assume that the potential is further like inside the corner. And I'm hoping that something could be done in the situation where it's only radially hurled, but not angularly hurled. So there could be jumps as long as they are not radial in the radial direction. And that would then allow a much better result for this kind of like piecewise constant potential unique determination. But yeah, besides this, I do have some other projects also going on. They're related to like measuring like hyperbolic inverse problems, but where you measure with noise, with white noise and so on. Maybe I could do a little advertisement here. So in case any of you have a postdoc looking for, or a recent PhD student who has recently graduated looking for a postdoc. So we recently got a lot of funding in Finland. There's many postdoc positions opening. And if you're interested in this kind of like scattering, inverse scattering topics, we have generous like two-year or more position available starting next year. So please spread the word.
Thank you so much. Thank you so much. Are there any other questions or comments, please? Any other questions or comments? If not, thank you very much, Emilia, for the very nice talk. Thank you so much. Thank you very much, everyone, for coming. Thank you.